Hello everyone, welcome back again on understanding Big O basics. So in the last part, what we covered was that what is Big O, wherein uh, we had gone through that Big O is used to judge the efficiency of a given algorithm, and it is also known as asymptotic runtime or runtime of an algorithm. Then we had gone through some of the most commonly used or commonly referred time complexities like order of n, order of 1, order of log n log n, order of n square to the power n square root of n. And we also uh, discussed that we can have multiple variables in our runtime and things like that. Then we had gone through big O, big omega, and big theta notation, what their meaning is. So essentially, big O is upper bound on the time, big omega is lower bound on the time, and big theta is just the tightest bound on the runtime. And we also discussed that whenever we are analyzing the efficiency or runtime of an algorithm, then we will always look for the tightest bound on the runtime, right? So in this part two, and even before starting this, I would like to share that some of the references while making this series is I have referred technical blogs on internet, and there is a very renowned book, Cracking the Coding Interview, 6th edition. So, and then I have also leveraged some of the generative AI tools to clarify some doubts myself and then explaining them here so that it becomes easy for everyone to understand the basics of Bigo. So with that note, let's go through the part two. So today we will be first talking about the best case, worst case, and expected case things in relation to big O complexity. So basically, uh, so suppose, or maybe let's start with like this. So best case, worst case, and expected cases describe the big O time for particular input source scenarios. Okay, so we had previously seen that big O, big omega, and big theta. So they describe the upper bound, lower bound, and tight bound on the runtime. So we can relate best case, worst case, and expected case here. So for example, let's say we have this function, right? Find number. So it takes an array, and we have to find this number or target in this given array, right? So here what we are doing is we are iterating through a loop from 0 to numbers dot length, right? -1 we can say, and then we are incrementing the index. So essentially we are iterating through all the elements of this array and checking if at current index the value equals to target, then we will just return the index. Otherwise, at the end, if we do not find it, then we will return -1, right? So if we talk about this, so this is kind of an algorithm, right? This is kind of a Java function, and we want to evaluate its time complexity, let's say. So now uh, the best case scenario, right? So best case scenario, what would happen is that uh, let's say we are having numbers as 1, 2, 3, 4, 5 in this array and we have to find 1, right? So when we will iterate through this array, so we know for the program will see, okay, at the very first index number is matching because it's 1 2 3 4 5, right? So in that case, it will quickly return, 0, right? The 0th index, because at the very first index we have this matching number of 1. So essentially this is the best case scenario, right? So it's like it's in the constant time. No matter how huge the array is, if the target is the first item, it always takes just one step. So we are just in the best case scenario. In the best case scenario, we will find the matching or target at the very first index of the given array, right? So that's why we said very first that best case, worst case, and expected cases describe the time for particular inputs or scenarios. So here the complexity, time complexity is order of 1 in the best case scenario, right? So then there is a worst case. So worst case scenario, what could happen? So in the worst case scenario, if we take the same example, so let's say my numbers are 1 2 3 4 5, right? And then my target is 6. So what will happen when this program will run? So it will go till the end and it will not be able to find the number, the target. So finally it will come here and it will return -1. So in this process, we have gone through all the elements in this given array. And finally, when there is nothing there matching the target, then we return -1. So worst case scenario is how many steps we took. So we took the same steps proportional to a number of elements in the given array. So if number of elements is n, so it's like directly proportional, steps are directly proportional to n. So in that respect, the worst case complexity is going to be order of n, right? So order of 1 in the best case scenario, order of n in worst case scenario. So that is what we are saying here. So if array has 1 million items, the loop must run 1 million times because it will not be able to find it till the end. So in the worst case scenario, algorithm has to do the maximum possible amount of work. Then expected case or the average case. So this is usually what happens on a typical random day, right? So our data is never like all, like it will always find the target at the first position or it will never find it. Usually numbers are in random. So we say the target is on an expected or average case, it will just be in the middle somewhere, right? So scenario is we search for random numbers that exist in the array. Sometimes we find them early, sometimes late. So that is the scenario. So what will happen is on an average, number will be somewhere in the middle of the array. So the loop will run roughly half times, right? So in average case, so we can say the complexity is going to be order of n by 2, but usually in time or space complexity, we always drop the constants. Okay, so basically it is going to still take order of n time. order of n. It is going to be its complexity. So what we are saying is, so the best case, worst case, and expected case scenarios are or describe the specific scenarios or for specific inputs. But as we discussed earlier, for the same code or for the same function, we always consider or we always focus on the tightest bound. What will be the tightest bound on this runtime? So it will be like it will not be able to find the number. So that is order of n. Okay. So that is what it is. So far we have gone through what the big O notation is. So I am again repeating it one more time. So far we have gone through what is big O and how it helps to measure the runtime of an algorithm. Then we have gone through that there are two parallel concepts. One is time complexity and one is the space complexity. And then how do we measure time and space complexity using big O, big omega, and big theta notations? And finally, we have understood that if someone asks us to determine the time complexity or space complexity, then we always look for the tightest bound on the runtime or tightest bound. So also it relates to the best case, worst case, and expected cases. So the best case is when algorithm is doing the minimum steps based on a particular scenario. Worst case is algorithm is taking the longest time due to due to particular input or data set, and expected case is average case. Okay, so now I will be covering the space complexity and some of the other things in later part of this series. So that's it for now. Happy learning. Thank you.